Nature often appears to follow mathematical laws, yet there are processes so complex that no algorithm can fully describe them. A mystery at the heart of the incomputability in nature paradox. How can something as fundamental as natural evolution, turbulent weather patterns, or even the behavior of individual molecules exhibit an unpredictability that no computer, no matter how powerful, can fully model? This paradox emerges from the idea that some aspects of nature may transcend computational reducibility, meaning that their future states cannot be predicted without actually running the full process in real time. Chaos theory provides an example. Even though weather follows physical equations, tiny variations in initial conditions, like the famous butterfly effect, can make long-term predictions practically impossible. In fluid dynamics, the movement of smoke rising from a candle seems random and impossible to predict precisely, despite being governed by physical laws. Quantum mechanics adds another layer of mystery, where the randomness in quantum state collapses challenges deterministic computation. Quantum superposition and entanglement create states that no classical algorithm can fully simulate in real time, leading to limits in quantum computing itself. Another case is biological evolution, where natural selection produces highly complex, optimized organisms over millions of years, yet no algorithm exists that can predict what mutations will be beneficial without physically simulating each step. The human brain and consciousness also present an example of incomputability. Why can't AI fully replicate human intuition, creativity, or the eureka moments of problem solving? Some researchers argue that our cognitive processes involve emergent, chaotic, or quantum phenomena that defy strict computational models. In celestial mechanics, predicting the movement of three or more gravitationally interacting bodies, the three-body problem, is unsolvable in general cases, meaning we must rely on approximations rather than exact solutions. Even the growth patterns of trees, the formation of snowflakes, or the flocking of birds involve complexities that simple equations struggle to fully model. Turing's halting problem suggests that some systems, like nature itself, might be running uncomputable processes, beyond what any equation or simulation can capture. If parts of nature operate in ways that are fundamentally uncomputable, it could mean that the universe is more than just a giant computer. It may be processing reality in ways that mathematics and computation alone cannot fully describe. But if we can't compute nature entirely, does that mean there are limits to science, or simply new frontiers waiting to be discovered? Some natural processes exhibit complexities that defy computational modeling, meaning no finite algorithm can fully describe their behavior. Quantum mechanics, turbulence, and chaotic systems often involve unpredictable dynamics that go beyond Turing computability, challenging the notion that all physical phenomena can be reduced to algorithmic processes. The three-body problem in classical mechanics, for example, lacks a general analytical solution, requiring numerical approximations instead of exact computation. Nature functions like an infinitely complex puzzle where each piece changes shape as you try to fit it, making exact solutions impossible. Alan Turing's halting problem states that no algorithm can universally determine whether any given program will terminate or run indefinitely. If physical processes have similarly undecidable properties, it implies that some aspects of nature may be inherently beyond computational prediction. Weather patterns, for instance, exhibit chaotic dynamics where small changes in initial conditions result in vastly different outcomes, making long-term forecasting infeasible. In trying to predict undecidable natural events is like attempting to read an infinite book where the pages randomly rewrite themselves. Chaotic systems, such as fluid turbulence and planetary motion, are highly sensitive to initial conditions, making precise long-term predictions impossible. Lorenz's butterfly effect demonstrates that tiny variations can lead to vastly different outcomes, making such systems chaotically irreducible. The double pendulum, for example, exhibits chaotic motion, where small differences in initial angles lead to entirely different trajectories. Chaos behaves like a domino effect in a dark room. Small nudges can cause unexpected and uncontrollable consequences. Gödel's incompleteness theorems state that any sufficiently complex mathematical system contains statements that are true but unprovable within the system. If physical laws follow a similar structure, it suggests that some truths about the universe cannot be formally derived. Quantum mechanics and general relativity remain mathematically incompatible, highlighting how a unified theory may involve undecidable or non-computable elements. Understanding the universe is like trying to assemble an infinite jigsaw puzzle where some missing pieces can never be found. Fractals, such as those found in coastlines, biological growth patterns, and turbulence, exhibit self-similar complexity at every scale. Many fractal structures require infinite calculations to fully describe, making exact computation impossible. The Mandelbrot set, for example, reveals infinitely complex structures no matter how far one zooms in. Nature's patterns are like an endlessly unfolding map. No matter how much you zoom in, there's always more detail. Quantum mechanics introduces computation beyond classical limits, as quantum entanglement and superposition allow for exponentially faster problem solving. Some natural phenomena, such as protein folding and photosynthesis, exploit quantum effects that defy classical algorithmic descriptions. Shor's algorithm, for instance, enables quantum computers to factor large numbers exponentially faster than classical computers, posing a challenge to cryptographic security. Classical computation is like following a single road, while quantum computation is like traveling on all roads simultaneously. Biological evolution is driven by genetic mutations, environmental interactions, and emergent behaviors that defy reduction to simple algorithms. Ecosystems, neural networks, and cellular processes exhibit complexity that resists full computational modeling. Protein folding, essential for biological function, is a computationally hard problem, requiring approximations even with supercomputers. Evolution is like an artist painting without a final design. Every stroke changes the outcome in unpredictable ways. The black hole information paradox questions whether information that falls into a black hole is lost, conflicting with quantum mechanics' principle of reversibility. If black holes fundamentally erase information, it challenges the computability of physical processes, implying that certain events may be permanently unknowable. Hawking radiation, for instance, theoretically allows black holes to evaporate, but whether information is preserved remains unresolved. A black hole is like a cosmic shredder. Whether the original document can ever be reconstructed remains a mystery. The fundamental constants of physics, such as the gravitational constant and the strength of electromagnetism, appear precisely tuned for life to exist. If these values were even slightly different, the universe as we know it would not form, raising questions about whether fine-tuning arises from an underlying, non-computable process. The anthropic principle suggests that our universe's physical laws are uniquely configured to allow for the existence of observers. The universe's laws are like a perfectly tuned symphony. If any note were slightly off, the music of existence would collapse.